I want to start with like the classical picture of learning theory, how we usually perceive it. So the simplest task you have data and you want to feed it, like x, y, everything is on the plane, x is scalar, y is scalar, you want to explain y through x. So what can you do? You can do one of two things. You can either choose a simple model to explain the data, like a linear classifier. You probably find the best linear classifier that explains the data, but the explanation would probably be very full. Or you can do the reverse. You can choose a very complex model. It will explain the data, but probably you won't generalize to other problems. So this is like a very toy example or toy problem, and you could say that classical learning theory kind of somehow tries to give rigor to this strategy of what can do or how can we fit a model, where the underlying message is that you have samples and you have the complexity of the model that you want for your data, and what you probably want to do is make sure that the complexity of the model will be simpler than the sample size. And then the rest of the theory is about making this more formal and making this more rigorous by actually defining what it means, the complexity of the model. So we have definition like VC dimension and Rademacher complexity. And then you also want to capture in this model more advanced topics than just linear regression in the plane, like regularization and margin theory and so on. But unfortunately, when we go to model and I, then things starts to seems to behave a little bit different. We seem to be training highly overcapacitated models. As far as we know, the complexity of the models is not smaller than the sample size. Okay, so it's really hard to explain in what sense, but because there is no real model for deep networks, but at least as far as we have some experimental evidence and also theoretical justification to say that probably the classical theory will not be able to explain so well how these models behave. Okay, so this was a tweet that was tweeted about a week ago and kind of went viral, and I think it kind of summarized everything I said so far. So,
pero ¿qué opina usted del gobierno de Zapatero? Pues igual que yo. ¿Y qué opina usted? ¿Qué opina usted? ¿Qué opina usted del gobierno canario? ¿Y de los ayuntamientos de la isla?
Yeah, so I'll add, the tweet said learning theory versus deep learning, saying that you can say whatever you want in learning theory about the capacity of the model, Rademacher, blah, 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 blah. Deep networks not captured by these notions. So overall, the recent theory has been about trying to bridge this gap with all these nice and vast solutions, like explaining through, okay, stability is a little bit older, and but notions like implicit regularization, inductive bias, flatness, sharpness of the minima, where somehow you try to develop a theory that doesn't only take into consideration the class that you want to learn versus the distribution, but you want to take a holistic approach, which says that somehow the algorithm also inhibits the capacity, somehow the loss landscape also adds something to the generalization, and somehow everything together kind of captures the model complexity. Now, okay, so this is deep network. What I've been investigating lately is another model of stochastic convex optimization. So what is stochastic convex optimization? It's pretty easy to describe. It's basically, you have a model where you have a distribution over convex functions, and you get to see samples of this data. And what you want to do is you want to minimize your convex functions. Now, you are probably familiar with a lot of examples of convex learning problems like linear regression, SVM, log loss. But it's kind of crucial for this talk that what we are looking at is problems that are, in fact, very different from these problems. And look at stochastic convex optimization in a general or broader view. So you could say it like this. So if you have the problems of deep learning and you have stochastic convex optimization, then yeah, there are these problems that are in the intersection, but kind of counterintuitive. What we are interested is actually all the problems that are outside of this intersection. The problems that are stochastic convex optimization are very, very different from deep learning. In fact, these problems are not even classification problems. And it might sound a little bit counterintuitive and not really clear why we want to do that, but here is the reason why. So it goes back to classical results about convex optimization, where the first result is a very nice result, which I'm sure everybody is familiar with, is that this is a setting where you can actually learn. Learning means you can actually find the minimizer, and we have a very good algorithm for this, very famous stochastic gradient descent. And it works in a setup where you have Lipschitzness and all in a dimension-independent scales. On the other hand, if you look at the Rademacher complexity, or you look at any of the complexity of the class, that in fact is dimension-dependent. Meaning, if we look at convex optimization infinite dimension, then you would have a case where you can learn, even though the complexity of the class that you are learning, if you want to learn it with ERM or something like that, that may be unbounded. So going back to the tweet, we in fact, in theory, we do have one theoretical model where we can actually see the same problem that we see in deep networks, and that is stochastic convex optimization. So from a theoretical point of view, the problem of learning theory versus deep learning is the same as the problem of learning theory versus stochastic convex optimization, where we can actually learn even though the Rademacher complexity of the class is unbounded, we cannot perform naive ERMs and so on. So what we've been doing in the last, I don't know, a year or two is we wanted to ask the following question. So if we have this model, the theoretical model where the phenomena that is so bothering to us in deep networks actually appear, let's take all the techniques that we've developed in the last few years, implicit regularization, algorithmic inductive bias, all these notions, and let us, can any of those explain what's going on in stochastic convex optimization? I mean, we know how to prove in stochastic convex optimization that you can learn, but can we use these techniques? Can we use regularization? Can we use inductive bias? Is it about the flatness or sharpness of the minima? And what I have now to tell you is basically some of the results that we've been having. So a first nice result is about the regularization or implicit bias. So it turns out that you can do the following. You can construct different functions. So these are vector fields of 4 different convex functions. Each of them is described is a vector field of the gradient of a convex function, where the global minima of these functions is all the same. It's all in the y-axis. You see where the dot red point is going. It's on this linear line. But you can make sure that SGD will go to a different minimizer for each of those functions. So what that means is that, to begin with, stochastic gradient descent doesn't necessarily go to the closest minimal norm solution, because I can make it go somewhere else. And I can make this even more general. In fact, no matter what type of regularization you might think of, I can cook up a convex function where stochastic gradient descent between 2 solutions which have the same minimal solution will go to the, let's say, less regularized solution, to the one that the regularized solution doesn't prefer. More than that, we can actually show that you can't even simulate stochastic gradient descent using some regularization, which kind of begs the question, if you can do that, then in what sense is it implicitly regularized? Or the same you cannot do with smoothing. So what does it mean? Basically, we can show the following. So if you compare SGD to GD, like full batch gradient descent, then you can actually show that stochastic gradient descent succeeds when gradient descent fails. Gradient descent doesn't generalize. It might overfit. And then you say, okay, can I fix it by adding some regularization? So I'll take a full batch algorithm that I added some regularization. Or maybe I smooth my loss landscape and then I applied gradient descent. I did something to the loss landscape and then I applied an optimization algorithm. Can I ever get the result that I get with stochastic gradient descent? And again, we can show separation. We can show that no matter what type of manipulation you do to the loss landscape, no matter how you try to stabilize it, the behavior of stochastic gradient descent is incomparable. It's much faster, and you cannot attain it by just adding regularization, smoothing, or doing anything like that. And now I'll talk about the result that I'm actually supposed to be working on now, which is we will probably call it benign underfitting. We're still working on the paper, but this is quite an amazing result where it kind of takes stochastic gradient descent out of the picture of all the method you might think of to explain generalization. So it turns out that if you go to the proof of stochastic gradient descent, it's kind of it's a very nice proof, but kind of curiously, it doesn't even use this showing that you have a generalization gap and you minimize the trainer. It uses some other technique, like it's called online to batch. And it turns out that this is not it's not a coincidence. In fact, stochastic gradient descent doesn't even try to minimize the generalization error or the train error. You can generate problems where stochastic gradient descent minimizes the test error, it learns, but at the same time, it doesn't even try to minimize the train error. It doesn't even try to control the capacity of the model it outputs, because it outputs a model that has large generalization gap, where the training error and test error looks completely different. So once you have this phenomena, it turns out you get this result that says that you will probably not be able to explain stochastic gradient descent using any technique that tries to bound the generalization error and train error, because these two quantities, they are just leading to vacuous bounds. They are never leading to the actual bound that explains why stochastic gradient descent is learned. So just, I want to summarize, because all of this was about different models in deep learning. So now comes the question, so what does it have to do with deep learning? So it depends kind of the relation between the two models of deep learning and stochastic convex optimization. And I don't know what's the relation, but it's one of two possibilities. And I think in any case, this result might be interesting. So the first result is that I wrote DP, it should be deep learning. I took it from a differential privacy maybe. So you would usually think of deep learning as kind of a more general setting or a richer setting than convex. You usually think of convex problems, these are easy, and then we have non-convex problems, we have deep learning. And this is where all the challenges are coming. But so if we think of it like that, as deep learning, a very general setup, and in it, there is stochastic convex optimization, or the loss landscape that we can achieve in stochastic convex optimization is part of what can happen in deep learning, then what happens is that basically, if we look at the techniques that we are currently developing in order to explain generalization, they are not going to work because they can't even explain what's going on in stochastic convex optimization. So we need to think of other techniques. We usually think of stochastic convex optimization as a problem that is easy, but if we look at the techniques that we're currently developing, the stochastic convex optimization is hard. It cannot be explained using the current techniques. But there is another option that deep learning and stochastic convex optimization, well, they are separated models. There is some intersection, we know, like STM and linear regression. Those are considered shallow nets, and they are also convex problems. But those are not the hard examples that I showed. Those are not the cases that I explained before. So there might be a separation between deep learning and stochastic convex optimization. But this is something that we need to understand, because currently we are not thinking of stochastic convex optimization as a challenge or as something that we need to separate from deep learning, because stochastic convex optimization is considered easy. It's considered something that we have good optimization algorithm and we can learn. But if we want to use the techniques that we're using now for deep learning, then we will need to find some separation between these two models. That's it. I hope I made it in time.
Thank you very much, Roy. And so we have time for a couple of questions. So one question is about this benign underfitting phenomenon that you discussed. A nice new phrase, which seems very intriguing. And I understand that your results and approach is mostly theoretical. Do you think that this is something that has practical implications and can be encountered in practice?
Right. So currently, I never heard of someone who tries to optimize the network and the trainer goes up. Usually, we try to minimize the trainer. So no, this is not a phenomena that you would actually see, but it is a phenomena that once it's there, it means that you won't be able to prove how something works without giving account to the possibility of this phenomena. And usually we disregard the possibility of this phenomena for a good reason, because we usually don't see it. And I can't tell you that we don't see it because we're not looking for it. I believe that we don't see it because it's probably not, it's not something that will happen in practice.
So there's still a gap between this result and really understanding what's going on.
Yeah, you could say that there is still hope. You could, if we can find a way to explain why these things don't happen in reality, we might have new tools and new techniques to explain generalization.
Okay, very good. And we have a question online from Alexander Molak, who says that he's using a graph attention neural network and he's typically getting validation error or prediction error that is lower than the training error. So maybe you have some idea why that would happen, or maybe this can be an example of your results.
Okay, so yeah, you know, maybe I was being maybe there is this phenomenon in reality. It sounds very interesting. I would be happy.
Okay, so if anyone has examples for Roy, please contact him and you can change science together.